Okay, we are going to try to complete the week 10 material with section 5.2, which is about projective transformations. Now, we've done a lot of work on the transformations that we can have of affine space, and we saw that if you want to preserve the line structure, then the types of transformations you get are affine transformations. So they will be an invertible linear operator plus a translation. Now, if you want to transform projective space in a way that preserves, obviously it has to, in the way that that points in projective space arise is as lines through the origin in an affine space. So you're going to have to send lines through the origin to lines through the origin. And you want to do that in such a way that it preserves the sort of the relationship between the lines. So lines in projective space become planes in the affine space, and you want to transform those so that they stay the same. And it turns out that if you want to do that, then what you need is an invertible linear operator acting on the affine n space, n+1 space that projective space comes from. So transformations of projective space arise from operators of am+1 which fix lines through the origin. Now there are lots of ways to fix lines through the origin. I mean, you could just pick two of them and swap them, but that doesn't. Those aren't the sorts of transformations that we'll be interested in, because they don't preserve the sort of fundamental relationship of the points with each other. So these will be simply invertible linear operators. So I think probably best to go straight in for an example here, which I will do actually after I've given the definition. So definition 5.10, projective transformations. So let T, sending a n+1 to a n+1, be an invertible linear operator. Then the map Pn to Pn, which takes the homogeneous coordinates x1, x2 up to xn+1, just to where their images will be under the map. So x1 dashed, x2 dashed, up to xn dashed, where t of x1 up to xn+1 So this point in the affine n+1 space, that just goes to these images. So x1 dashed up to xn, that should be an n+1, n+1 dashed. Okay, is called a projective transformation. Let me just see if I can get that a little bit more. Great. Okay. One should check that this is well defined. So if I take another representative of the same line, so that would be a scalar multiple of this, that it does go to a scalar multiple of this, right? So that it doesn't matter which representative you choose, you always get the same line in the image and therefore the same homogeneous coordinates. But that is true because t is linear. So so if I multiply the point by lambda, then t of lambda times that point is going to be lambda of t times that point. So that tells you that it is well defined. Okay, so let's look at example 5.11. So this is just where we're going to look at the case where n is 1. So consider P1, the points of it, and a projective transformation of P1 is just given by a matrix, which I'll write as alpha, beta, gamma, delta. And what does it do to the points? So in homogeneous coordinates, if I've got a point xy, I just treat that like a vector, xy here, and then apply the matrix to it. So this goes to alpha of x plus beta of y colon gamma of x plus delta of y. Okay, so that's what it is. But what's sort of interesting is what happens on the affine chart, because these projective transformations can send points off to infinity and bring points back from infinity. So let's see how that works. So in the last affine chart that we're writing as A22, what happens? So the points there are simply x over y1. So we assume that y is not equal to 0. So the point xy just looks like x over y. Sorry, it has coordinates. Well, it's a single coordinate because it's one-dimensional, so it has coordinate x over y. Because we assume that if y is non-zero, we can divide by it, and then that's where we get our chart. So where does that go? It gets mapped to, well, we've just written it down. Alpha of x plus beta of y is where x goes, and gamma of x plus delta of y is where y goes. Right, so that gets mapped to the ratio of these points. So you have alpha x plus beta y over gamma x plus delta y. Now, if you want to write that in terms of the point xy, we have to divide through by y. So we get alpha x over y plus beta x over y, plus beta over gamma x over y plus delta. Right, now this is what's called a rational map, because it is the ratio of some points, but it's actually not fully defined on the affine chart here, because you can take a value of x over y, which sends this bottom, so the denominator, to 0. So note that this is only a partially defined map. So if x over y is equal to, we want this to be 0, so minus delta over gamma, minus delta over gamma, then the denominator above is 0. And in that case, you end up sending x over y to the point at infinity. In fact, x over y gets mapped to the point at infinity. Now you can kind of make sense because there is a single point at infinity, you can actually work with that and put it in instead of x over y here. And what happens is, and it is an abuse of notation, but it does work. You can see the point that you get that infinity is mapped to. So it's actually mapped to the point. Somehow the beta and the delta don't really matter because these are infinity, and so you can actually make sense of what this fraction is when you use x over y infinity. So by contrast, if x over y equals infinity, we get infinity mapped to alpha infinity plus beta over gamma infinity plus delta, which is equal to alpha over gamma. And at the level of homogeneous coordinates, this makes sense, because the point that you don't get in the affine chart we're looking at is where y is 0. So so this makes sense because so infinity is really equal to the point where y is 0, so we can call it 1 colon 0, and that indeed does get mapped if you apply the original matrix to 1, 0. You do indeed get alpha gamma, which is on the affine chart. If gamma is non-zero, it goes to alpha over gamma, which is equal to alpha over gamma. Right. So so I kind of covered a lot of what's in remark 512. So by abuse of notation, we can consider this point 1, 0 as infinity, and then P1 is equal to A1, you can even write isomorphic if you like, union with this point at infinity. Right, but if you're not working with a projective line, there will be more than one point at infinity, and so you can't just use it like that.